So we'll just recap what we've done so far. Okay? So we started story with the graphical analysis. So graphical. So position analysis. Okay. So this graphical position analysis we have done only for the 4-bar mechanism. Okay. So wherein what are the values given? So given A, B, C, and D, and theta. So we plot the mechanism to scale, then find theta P and theta. Okay. So after the graphical position analysis, we can also do graphical position analysis by analytical method. So position analysis by analytical method we have done only for the assignment part. Okay. So normally you will not be asked in the exams position analysis by analytical method. So position analysis so by analytical method. Okay. So only for assignment. So this is the first part of your second assignment. So all the required equations for the position analysis so already available in the session 4 notes. After graphical position analysis, we do graphical velocity analysis. So graphical velocity analysis. So the graphical velocity analysis will be done by 2 methods. One is the velocity polygon or the relative velocity method. So the relative velocity method. And IC's method. Okay. So the analytical method only for assignment. That means you will not be asked any question related to analytical analysis, either for position or for velocity or for acceleration also. So the next one is the graphical acceleration analysis. So here we have done only the relative acceleration method. Okay, so by the time when you start the relative acceleration method, so you know so what are the known parameters? You know A, B, C, D, you know theta 2, and from graphical position analysis, you know theta 3 and theta 4. Omega 2 angular velocity of the link 2 will be given. Okay? So then you will be calculating velocity A, velocity B, velocity B to A, and omega 3 and omega 4. So you can find out all these things from the given information. So that means by the time you start acceleration analysis, you know all these things. In addition to these things, gamma 2 is, alpha 2 is given. Angular acceleration of link 2 will be given. So all these things we know. So normally when a mechanism is in operation, so the points on the linkage mechanism will have velocities. Okay, linear velocities. The points will have linear velocities, whereas the links will have only angular velocities. So the links will have only angular velocities. Now after this what? So once you complete your position analysis, velocity analysis, acceleration analysis, so the next part is the force analysis. Okay. So next we look into the force analysis. So by the time we start the force analysis, that means you know all these things. So you know, you can plot the mechanism to scale, you know the velocities of points, you know angular velocities of the links, and also you know the accelerations. In addition to all these things, you also know the mass of the links. So because when you calculate forces, you must know the mass moment of inertia. So mass moment of inertia depends on the mass and also the distance from the axis of rotation. So the r part. Okay. So when you start force analysis, in addition to all these things, you also know the geometry of the links, then the masses of the links. Okay, so that is mainly to calculate moment of inertia. Okay, so for force analysis, okay, in addition to the above, so mass of the links will be given. So we know the masses of the links. Alright, so this is the background what all we've done so far. So we know that the Newton's second law. Okay, so what is Newton's second law? Anyone? Simple terms.
Force equals to mass times acceleration.
So the force is equal to mass times acceleration. So in fact we write the second law as the net force acting on a system. Okay, that means the sum of all the forces. So there may not be only one force, there could be several forces. We need to know the resultant force or the net force. So the net force acting on the system, because this is a vector, we write it as mass times acceleration. Okay, so this is again a vector equation. So we can formulate it with the scalars equations from this. So we can write the scalar equation like this. So sum of the forces acting along x. So we can write it as mass times acceleration along x. So now this part is basically a scalar formulation. So the x component of the force we are equating with mass times acceleration of the x component. So similarly we can write sum of the forces acting on the system is mass times acceleration of y. Now, are there any other equations related to Newton's law? thermodynamics knowledge, so you can understand that these two equations are valid only when the force is acting at the mass center. Okay? So for example, for any system, let us say you have any system like this. Okay? We can apply these two equations only when the forces are acting at the mass center. So that means we consider that the entire mass is concentrated at one point. So therefore we consider this as the point mass. Okay, so but there will be other instances. So for example, if the force is not acting at the mass center, but let us say acting away from the mass center, then how to write the equation? So for example, you consider instead of here, the force is also acting here. So then these two equations are not valid in this case. So these two equations are valid only when the force is acting at the mass center of the system. But when the system and the force is not acting away from the mass center, then the moment of force or the torque will affect the movement of the system. So in that case, we write because the body is subjected to rotation action. So what is the formula when a body is in rotation? So simply we know that a body is in rotation. Okay, so the linear displacement is r times angular displacement. Okay, so for example, if you consider let us say a point, so which is in rotation, we consider this is moving in a circular path. Okay, so we consider this is r, the position of the point, and this is also r, the position of the point. Then this is the angular displacement. So the linear displacement will be here on the circular path, the outline of the circle. So this is your S, linear displacement. Okay. So the relationship between S, R, and theta. So we can write S is equal to R into theta. So similarly, the velocity of the particle can be written as R into omega. So when theta is the angular displacement, omega is angular velocity, then acceleration we can write it as r into alpha. Alpha is the angular acceleration. So we can write theta is angular displacement. So v is angular velocity, and alpha is angular displacement, acceleration. So this is how we can relate the linear variables displacement, velocity, and acceleration with angular variables theta, v. I'm sorry. Here I wrote v, it should be omega. Okay, angular velocity, omega. Now, when a system is having, so now the force we can write the net force is mass times acceleration. Now this is for linear motion. Now for rotation, mass is replaced by another quantity. What is that quantity? So for linear motion, we talk about mass. So when the system is having a rotation, so the mass is replaced with a variable. What is that?
Inertia.
Hmm?
Inertia.
Yeah, inertia, what inertia? So basically, mass is a measure of inertia. Okay, so inertia is the quantity. So how do you measure inertia? The mass. How mass is related. So inertia is inability of the objects to move on their own. Objects cannot move on their own. So they need an external force. So that means the masses will have inertia. Okay, so similarly when a body wants to rotate, it cannot rotate because it has a rotational inertia. So the rotational inertia, so for linear motion, the mass, so for angular motion, the force is replaced with the moment of force, or which is known as the torque. So for example, if you consider a body like this, okay, now we consider this is the position vector, let us say R bar. Okay, so if a force is acting here, okay, so let us say a force is acted upon here. Okay, so this R bar and force will cause the object to rotate or produce a torque, okay, so which is written as I into alpha. Tau is the torque acting on the body. So torque, or we can also call it as force of rotation. So effect of force on the body, but it does not produce a linear motion, but it produces a rotation. So angular displacement. Okay, so I is the mass moment of inertia. So alpha is your angular acceleration. So now when we consider a linkage system or linkage mechanism, so the mechanism has points, okay? So the points have linear velocities, okay? The links have angular velocities, okay? So the system is having a combination of linear motion plus rotation, okay? So for linear motion, we can write the two equations, sum of the forces acting along x and sum of the forces acting along y. So we can write m into ax or m into ay. So in addition to this, because the system is also in rotation, then we need to write the torque acting on the system is instead of I, we write Ig. So this is the mass moment of inertia with respect to the centroid. Ig is the mass moment of inertia, because inertia always refers to an axis. Okay, so point of reference. So here the point of reference is moment of inertia with respect to the centroid. Okay, that's why Ig. So you know the parallel axis theorem, right? So we write I is equal to, so that is inertia with respect to any other axis other than the centroid will be Ig plus m into d square. So where d is the distance from the centroid to the new axis. Okay, so I represents inertia with respect to any axis. Okay, Ig is inertia with respect to the centroid. Okay, m is mass, d is inertia with reference to any other axis. Okay, the distance from the centroid to that particular axis. Now, for example, let us take a link like this. So, with respect to the centroid, Ig. Okay, so the moment of inertia you know from the property tables. So, objects. So you know the properties of the geometries based on the standard tables. So you can get the formula for IG. If you know the geometry of your link, okay, then you know the formula. Okay. So now let us say your axis has not at the centroid, but normally the links are connected at the end of the link. Okay. So the point will be here. So in this case, now the D is this distance. So now let us say now you need to know inertia through this axis, because the links rotate not with respect to centroid but with respect to the point of pin joint. Okay, so now we need to calculate inertia with respect to this point. So in such a case, we apply this parallel axis theory. Okay, so inertia through this axis is now inertia through the centroid, which we know the formula plus m d square. Okay, so for example, if it has a length of L, let us say, okay, the height is L. So the formula for this is 1/12 m L square. Now, because we want to calculate inertia through this point, okay, so we apply the parallel axis theorem. So then we write m. Now what is d now? Anyone? What is d value?
L divided by 2.
Yeah, L over 2. So we can write L over 2. That's fine. So now inertia with this new axis is 1/12 ml square plus m into L by 2 square. Okay, so you must have done this in your engineering dynamics assignment too, when you have done your slider crank. Alright, so now when you are doing dynamic force analysis of linkage mechanisms, so now the scalar equations will be the three. Okay, so what are those three? You can see here. Okay, so when a link is in rotation, so we can write so some of the forces acting with respect to x-axis, mass into acceleration of x, and some of the forces along y-axis, mass into acceleration of y, and similarly the total torque acting on the system. Okay, the total torque or net torque is Ig into alpha. Now, what is this torque? So torque is the rotational force line. So if you look here on this figure, so just focus. Okay, so we are writing now based on this. So the torque is the cross product of R bar and F bar. So torque is basically the vector product of the position vector and the force vector. So the magnitude of this you can write it as Rf sin theta. So where theta is the angle between the force and the position vector. So you can also write the torque in vector form. So if you recall, torque can be written as R bar cross F bar. So you can write this in vector form as the unit vectors taking. Then we can write the position of x, position of y, then the position of z, then the force component x, force component y, and the force component z. So you can find out the cross product or the torque acting on the system or dot cross F. So in vector form, you can write like a determinant 3 by 3 determinant. So the first row is the unit vectors. So the second row will be the coefficients of the position. So position vector. So coefficients of the position vector means this Rx, Ry and Rz. So force, again the third row is the component of forces, X component, Y component and Z component. So you can evaluate this determinant and you can find out what is the torque acting on the system. So simply the magnitude, you can write it as the magnitude of torque will be Rf into sin theta. So this is the magnitude. So when you are doing the dynamic force analysis, so we'll be applying basically the three equations. So as shown here. So these are the three equations governed. So sum of the forces, so the sigma. So sum of the forces acting here along x-axis. Sum of the forces acting along y-axis. Then sum of the torques. Okay. So sum of the torques acting on the system is Ig. So Ig is the mass moment of inertia. So generally the mass moment of inertia will be m into r square. So the unit is kilogram meter square. Alpha is the angular acceleration. So now we try to analyze for a linkage mechanism, okay, link by link, okay, how the force analysis can be done. So now you can see, okay, a link in pure rotation. So you can see there are many things shown here, right? Okay, so a simple link is this. Okay, link 2 you can consider. Now it is shown with respect to a global coordinate axis. Okay, the mass center of the link, CG, center of gravity. Okay, so this is the mass center. Okay, so the mass of the link is F2. So you know theta 2. Okay, so Ig2 refers to inertia of the link with respect to the mass center. Inertia of the link with respect to its mass center. Okay, so theta 2 is its orientation. So now this link is having an angular acceleration and angular velocity as shown in counterclockwise. Okay, so now we need to calculate what is the force acting on this at point P. Okay, so this is the point P. So we know omega 2, we know alpha 2. Okay, S is, what is S here? So the distance from the origin to the centroid. Okay, so the length of the link is 10, so S is nothing but 5. Okay, so the distance to the centroid. So now we move on to, we are drawing the free body diagram for this. Okay, so when you're drawing the free body diagram, first we'll draw the free body diagram for the pin joint at O2. Okay, at O2, so there is a force on 2 from 1. So 1 is your ground link. So we are drawing the free body diagram for the ground link. Okay, so ground link, there is a force acting on link 2 from 1. So this we write it as F21. So there is only one force which is acting as shown here at link 1. So link 1 is the ground link. So now we move on to link 2. Okay. So link 2 is having a rotational force, a torque. Okay. So this is torque of 1 on 2. Okay. 2 is your link. Okay. So this torque is related to, because this is connected with the pin at link 1 here. So there is a torque, rotational torque acting, which is torque 1, 2. Okay, so then there is a force of 1, 2 here. So F21 is equivalent to F of 1, 2 negative. Okay, so these two forces are equal and opposite. So when you look at point on link 2 at point O2, so there is a force 1, 2. And force 1, 2 and force 2, 1 are equal and opposite. So, but when you draw the free body diagram, you need to show the arrow like this. Okay, similarly for link 2, so F1, 2, and again at point P you have FP. Okay, so there is a force acting at the pin joint here. So now what are the other things we have? So the two important things which you can see is R12. So R12 is the position of link 2, okay, from position of 1 from 2. So this is actually from the center of gravity of the link 2 to the point 1. So this is the position vector. You can see the arrow here. Okay, it is measured from the center of link 2. So similarly, this is the position vector RP. So from the center to the point P, the distance. Okay, so we are now having two position vectors. One is R12, the other one is RP. Then two force vectors. One is F12, the other one is FP. And there is an external torque. So this torque is an external torque. So which is torque 1. Okay, so this is the free body diagram. So for link 1, this is the free body diagram. So we are showing both the position vectors and the force vectors and any torques. So now you can see the small x and small y is the local coordinate system. Okay, so the global coordinate system is shown here. So this one you can have. So local coordinate system can have from any point. Alright. So is that clear, the free body diagram? Okay. One important thing is that there are 3 or 4 different types of linkage mechanisms. So for these 3 linkage mechanisms, we will be defining the force analysis. Okay, and one of the question will be asked in exams. So normally there are 3 or 4 which are available in your learning guide, and also Dr. Firoz will be going through, and normally one of that question will be asked. Alright, so if you can understand, the important thing is every link you need to draw the free body diagram. Now for link 1, link 2 we have done. Now only for link 2, so we'll end up writing 3 different equations. So when you add another link, you will have 6 equations. So when you have another link, you will have 9 equations. So normally for a 4-body linkage mechanism, so 4-bar linkage mechanism, you may end up with 8 or 9 different equations. And these equations will put in matrix form. So that means you will have a 9 by 9 matrix or 8 by 8 matrix. So depending again on the alignment of the matrix. So therefore, you will not be doing any calculations related to force analysis. Of course, you are going to do for your assignment, but not in the exams. Because normally in the exams, the minimum 4-bar linkage mechanism, you will be ended up with a 9 by 9 matrix. 9 by 9 matrix is humanly impossible to solve unless until you use any software, either MATLAB or DAV or use some software. Okay. So now let us see how we can write the equations for a simple link notation. So related to the force one. So we can write now for the link sum of the forces acting on the mechanism. So sum of the forces acting on the link will be Fp plus F1, right? So these are the only 2 forces. So sorry. So these are the two forces, F12 and Fp. So what is the total force acting on this link? So we need to just add up this force. So it is a simple force addition of the two forces. Okay. And you can write this as mass into acceleration. So mass is for link to M2. Now acceleration, which part of the link acceleration? So we always consider the link as point mass, and we consider that entire mass of the link is concentrated at this point, center of gravity. So therefore, we consider the acceleration of this point. So this acceleration of the centroid of the link, AG. So does this make any sound? It makes sense, right? So the total force acting on the link will be, so sum of the force at P plus force 1, 2 is equal to M2 into acceleration of the centroid. So we consider that now the force and accelerations with respect to the mass center. Okay. But now if you consider the torque, so as I said, the torque is the cross product of R bar and F bar. Right? If you recall the diagram which I have shown, so torque is R bar cross F bar. Now there is an external torque T12. So now we are writing the total torque acting on link 2. So the total torque acting on link 2 will be, so external torque 1, 2, so that is shown here T12. Okay. Then what is the torque developed due to this force? Okay. And what is the torque developed due to this force? So we have R12 cross F12, then RP cross FP. So therefore we can write, so the sum of the torque acting on the system link 2 will be external torque 12 plus R12 cross F12 plus RP cross FP. So this is the total torque. And this total torque we can write it as IG, that means mass moment of inertia of the centroid of the link 2 into alpha. So here 50 we need to write alpha 2. Alpha 2 is the angular acceleration of the link 2. Okay, so the first one is basically a vector equation. Okay, so we can write this vector equation into scalar equations, okay, by taking the x component and y component. So therefore, the first equation, which is a vector equation, we are splitting this into two scalar equations. So we can write it as the Fpx component plus F12 x component should equal to M2 into acceleration G x component. So similarly, the y component of P plus 1, 2 force 1, 2 y component should equal to M2 into acceleration of G1. So the acceleration of the centroid y component. So this vector equation we have written in terms of two scalar equations. So now we can look into this equation. Okay. So this equation requires some treatment. Okay, so there's I just rewrite here. So the sum of forces acting on the system is equal to Fp plus F12. So this one we are writing in scalar notation like two equations. So we write Fp x component plus F12. So we write F12 x component. We can write mass 2 into acceleration of G x component. So then you can also write for the y component. So F_y plus F12y is equal to F2 acceleration of g y component. So you can consider this as equation 1 and equation 2. So the next equation is related to the torque. So the torque 1, 2. Okay. So plus, okay, the cross product of 1, 2 and force 1, 2. So this is a vector equation. So plus, so the position vector are P cross F. So this equal to Ig into alpha. So basically this is a vector equation. So this vector equation we need to convert into a scalar equation. Okay, so to convert into scalar equation, so we write it requires some amount of derivation. Okay, we take the first one, R12 cross F12. So we can write so R12 x plus R12 y cross F12x plus F12y. Okay, so I'm writing the vector R12 bar as x component plus y component. So similarly F12x, F12y component. So now I can do the cross product. Okay, I can multiply. So now once I multiply this, how much I get? R12x cross F12x. So plus R12x cross F12y. So plus R12y cross F12x. So plus R12y cross F12. So we can expand this term, okay, like this, writing x component and y component, then we multiply. Now, what is the cross product of R12x and F12x? Any idea? So the cross product of two parallel vectors x and x, right? So both are in the same direction. So the position vector R12x component, the force vector F12 also along x-axis. So what is the cross product of two vectors? Now, for example, if you have a bar and b bar are two vectors, so the cross product of these two vectors we write it as AB sin theta, the magnitude, right? So theta is the angle between the two vectors. So when theta is 0 degrees, so what is A bar cross B bar?
Zero.
So 0 means two parallel vectors. So the two vectors are parallel to each other. So the cross product is 0. Okay. So now you can see the cross product of R12 and F12x. So because these are the two parallel vectors, so the cross product is 0. So similarly, R12y, F12y. So the cross product is 0. Now, what is the angle between x and y? So here this is x component and this is y component. So the angle between them will be 90 degrees, right? X and y. So sine 90 is 1. So when theta is 90 degrees, so when theta is 90 degrees, A bar cross B bar can be written as AB.
So I can't see.
Okay, so similarly, when the same thing, B bar cross A bar can be written as minus AB. Okay, so now if you see here, this vector we can write in a scalar form. Okay? So we can write in a scalar form simply as this portion. We can write R12x okay, into F12y. Now, this one is y bar cross x bar. Okay, so this one is y bar cross x bar. So we need to write minus AB. So therefore, you can write negative R12y into F12x. Okay, so what we have done, we have just done one term. So this is a vector notation. So this vector cross product can be written like this. Okay, so this is a scalar equation now. Okay, so next, similarly, we need to do the RP bar cross FP bar. So this portion, okay, RP bar cross FP bar. So this one we can write it as okay, RPX into FPY minus RPY into FPX. So basically we are writing the vector equation and converting it to scalar equation. Okay, so now the third equation, so we have written equation 1 and 2 like this. Okay, so these are equation 1 and 2, scalar equations. So now this is our third equation. So now we are converting this equation into a scalar equation. So we can write now the final equation, the third equation, as in scalar form. So T12 plus R12x F12y minus R12y F12x okay, plus RPX FPY minus RPY FPX. So the whole thing is equal to IG into alpha. So this will be our third equation. So we can now for its link 2, we have ended up writing 3 equations. And these 3 equations, we have 3 unknowns. So we can put these 3 equations in matrix form. Okay. So let us say we have 3 simultaneous equations, let us say a1x plus b2y plus a3z, b1x plus b2y plus b3z, c1x plus c2y plus c3z. Here, let us say this is p1, p2, p3. Can you see? Now, 3 simultaneous equations. So we know a1, a2, a3. We know b1, b2, b3. We know c1, c2, c3. We also know p1, p2, p3. Now, what are the unknowns? So the unknowns are x, y, and z. So now these 3 equations we can write in matrix format. So we can write simply a coefficient matrix a1, a2, a3, then b1, b2, b3, then c1, c2, c3. So this is a 3 by 3 matrix. Then you have a column matrix x, y, z. And you will have a column matrix b1, b2. So these 3 equations can be written in the form of matrix multiplication like this. So here you know this matrix, you know this matrix, so then you need to calculate the x, y, z components. So you can use any inverse matrix method and you can solve the 3 unknown quantities. Okay. So this is just the background because we are going to write our 3 equations into a matrix format. So what is the basis for writing? So we can write the 3 simultaneous equations in matrix multiplication format because that is the easy way to solve. So similarly you can write the whole thing, you can write matrix A into matrix X is equal to, let us say, matrix B. Okay, so matrix X can be written as A inverse into B. So this solution part we are not doing it, but only we are writing. We are going to derive the force equations for each link. Okay, so depending on the number of links and depending on the conditions, okay, the equations will slightly change, and we combine all the equations and we put in one matrix format. So because 3 equations, 3 unknowns, so we will be ending up 3 links, the 4 links will have 9 equations. Alright, so I go back to this one. So our 2 equations are this. So these are the equation 1, equation 2, and this is our equation 3. Okay, so now I'll show the same thing here. So now you can see the 3 equations here. Okay. So what is the difference between this set and this set? So the top 2 equations are in vector form. So we are converting this vector form equations into scalar equations. So scalar equations means we can just treat like algebraic equations and we can solve them. Vector format you can't do unless until you convert them into scalar format. Okay, so this equation when you convert into scalar format you end up like this. So I explained how the cross product R12 cross F12 will give this value. So similarly RP cross FP will give you this set. Okay. So now these 3 equations you can now write in matrix format. So when you write in matrix format, okay, so F12x, F12y, the unknowns are the x components of F12x, F12y and T12. Okay, so you can write the first equation F12x is equal to M2AGX minus FPX, right? So the first equation, okay, so you can write it as so for example the first equation you can write it as F12x is equal to M2 AGX minus FPX. Okay, so here the coefficient for F12x we can take it as 1. So is there any y component here? No z component. So the coefficient matrix here for this will be x is 1, y is 0 and z is 0. So when you write F12x here, okay, so the coefficient matrix will be 1, 0, 0 because only x component is present. There is no y component and z component. So therefore you can write now the first equation. So this first equation you can write it as 1, 0, 0 into F12x is equal to M2 AGX minus FPX. Okay, so now come back to the second one. So second one we can write FPY is equal to, so FPY is equal to, so you can write M2 AGY minus FPY. F12y, right? So this is F12y. So FPY. Now here there is no x coefficient, so 0. Y coefficient 1. And there is no z, so 0. So you will have the second row, so 0, 1, 0 multiplied by F12y. So is equal to, you can write M2 AGY minus FPY. So that is the second one. Now similarly the third expression, so T12 R12x R12y. So you just write everything IG alpha minus the y RPX FPY, okay, RPY into FPX. So this third equation you can write the coefficient for F12y will be R12y. Okay, so the coefficient for R12x will be F12. R12x will be coefficient for F12y y. So here y you are getting here, so it goes with a negative sign here, r1 to y. So here negative. Okay, for tau the coefficient is 1. So now the whole thing you can write as the third row here. So basically these three equations can be arranged into a coefficient matrix. Now what is the coefficient matrix? 1 0 0 0 1 0. Then the coefficient for the third one will be r1 to y, r1 to x, and 1 1 will be for this. Okay, so the whole term you are taking the other side, ig alpha minus this. Alright, so now for link 2, the unknowns are the f1 to x, f1 to y, and the external torque 1. So what are the things known? We know everything. Okay, so we know r1 to y, r1 to x. What is r1 to x? So the x component of r1 to. So that means if you know the length of link, so and the angle theta 2, so you know both r1 to x and r1 to y. Okay, ig we can calculate based if you know mass and if you know the length of link. Alpha value will be given to us. Okay, so similarly the x component of the rp, position vector rp, then the force vector, okay, xy, force vector at point P we are able to calculate. Okay, so we know this matrix C, we know matrix A, then we need to calculate matrix B. So that means we need to know the F12, the force acting on 1 2 and the torque acting on 1 2. Okay, so if a simple link is given like this with the given dimensions, so there's an example in the textbook, you can go through the calculations. But again, it requires you to solving a 3x3 matrix. So generally, the calculations will not be asked, but the derivation will be asked. So this is only for one link, yeah? Only for one link. So only for this link, link 2, we have derived the three equations and we have written in matrix format. Now, let us say we extend this for F4 bar linkagement mechanism. Okay. Now this is basically a 3-bar linkage mechanism. Okay. So you have link 1, link 2, link 3. Slider is link 4. Okay. So this is also ground. So basically there is no slider here. So ground link. So ground link, the free body diagram is F1. 2 1 is equal to negative of F1 2. Okay. Now link 2 is very similar to what we have done. Okay. So you can say link 2 is not a very rectangular link, but it is a ternary link, a triangle shaped link. Now the centroid is given here. So you know the centroid, you know the dimension. So you know R12 is the distance from the centroid of link 2 to point 1, a joint. Okay, so this is R32. Okay, so because here this link is connected to link 3. Okay, so now this is the position of 3 from link 2. Okay, so this is your link 2. So link 2 is connected to link 3 at this pin. Okay, so therefore from the centroid to this distance is written as position of 3 from 2, R3 to R3. So similarly from now you can see the link 3 here. Okay, so now the centroid of the link 3 is shown here. Now this vector is Now position of 2 from link 3. So position of 2, 3. So we are locating towards position of 2 from link 3. Okay, so similarly this is the position of 1. So 1 is your ground link. So from link 3. So R1. So position of 1 from link 3. So this is now a point P on link 3. So this is just position of P. So similarly the force acting at this point is P. Okay, so in the exams you will be given a 4-bar linkage mechanism. So first thing, you need to draw the free body diagrams, identify all the position vectors, force vectors, name them accordingly. So please pay attention. Anything which is not clear to you, let me know. So you know the angles theta 3, theta 2, we know all these angles. Why these angles are required? Why theta 2 is required? Now, if you know theta 2, then you can write what is R12 x and R12 y. Because R12 is just the distance. So R12 x means, so this distance multiplied by cos theta, theta 2. So what is R12 y? So this distance multiplied by sin theta 2. So x component, y component. So x component is, you know how to resolve a vector, right? In terms of x and y component. So similarly, R32. So if you know the orientation of this link, then you know its x component and y component. So this is R32, right? This vector. So x component is R32 into cosine of this angle. So the y component is R32 multiplied by sine of the angle. So these are coefficients which we know. So we are locating the centroid for link 2, centroid for link 3. So consider mass is known, and all the geometry is known. Okay, so the force acting on this point 3, 2 we can calculate. Okay, so now the free body diagram part is that clear to you? So there is a 4-bar linkage mechanism, so you are going to draw for 4-bar. So the good thing is you need to look only 3 or 4 places like this. So one of the case will be asked. And if you can understand this mechanically, you can write down. Now first, any questions on the free body diagram? And the notations why we are writing F21 is negative of F12. So if you see here, this is the force of 2 from 1. So 1 is ground link. Okay? Now the same thing when you see here, so this is F12. So force on 1 from link 2. Okay? So this is force on 2. Okay. This is the position of 3 from 2. So force of 3 from 2. So this is the force acting on 3 from link 2. So here, this is the force acting on 1 from 3. Okay, so from the ground link to link 3. So it is directed to link 3. So now we need to write down the equations. So first we write sum of the forces is mass times acceleration. Next we write sum of the torques is Ig into alpha. So these again the force equations we write in terms of the components. So we write F12x plus F32x for this is for link 2. Okay, so x component of the force 1, 2, then x component of the force 3, 2. Okay, so you can see these are the two forces on link 2. So we can write m2 into acceleration of the centroid of link to x component, then acceleration of the centroid of the link to y component. So the y components. Then again the total torques acting on the system. So P12. Now here straight away we are writing the scalar notation. Okay, so basically we need to write R12 cross F12, then R32 cross F32. So because these are the vectors, right? Vector cross product we must write. And earlier I have just explained to you. So this cross product of 1, 2 and F12 we can write like this. So the whole thing in scalar notation is result of the cross product of the position vector 1, 2 and the force vector 1, 2. Okay. So similarly the cross product of 3, 2 and F32 will give this. So the whole thing is inertia of the link from the centroid link to IG2. Alpha 2 is the angular acceleration of link 2. Okay, so we can write these three equations for link 2, then similarly for link 3. Okay, so link 3 also we write the three equations. Okay, so link 3 there is no external torque. So the torque is mainly due to the cross product of position vector 1, 3 and force vector 1, 3. That is this. Then for position vector 2, 3 and force vector 2, 3. So these two vectors. So that is this. Then position vector for RP and FP. So this factor. So because cross product is nothing but R bar cross F bar. So how many position vectors are there? 3. How many force vectors? 3. So you will have the torque produced by the cross product of the position vector and force vector. Alright, so you get to derive the same thing. If you know the logic, then it is just mechanical. So after that, combine all these things. Okay. So here, if there is a friction coefficient is given, okay. So then we can write the frictional coefficient here. Then you can combine all these three equations. Then we can write in matrix format. Okay, those 6 equations you can write in matrix form, 6 by 6 matrix like this. Okay, so we need to combine all the 6 equations. So this will be the final answer for a 3-bar linkage mechanism. So normally in the exams you will be asked 4-bar linkage. So 4-bar linkage is something like a slider crank. If you recall, you have done this slider crank in engineering dynamics course. The same assignment question. Okay, so you will find the complete solution of this, but in the force analysis by analytical method. So here, so this is the slider crank, right? So this is the crank, okay, connecting rod, and this is the slider piston. So 4-bar linkage mechanism. Okay, so the probability of getting this question is 33%. So but you will be getting only for 20 marks, and you need to write down, draw the free body diagrams clearly, write down the steps clearly, then give the matrix format clear to get full marks. Okay, so see the free body diagram for link 1. Okay, so this is for the crank link 2. So this is for the connecting rod. So this is for the piston. Okay, so only thing is you have to spend few hours to figure it out yourself, then try to formulate your own way to remember and reproduce things, because no more online exams, right? So you will be having supervised exams, and the questions will be simpler. The questions will be generally simpler for supervised exams. Okay. So this is the book considered as the Bible for this mechanics of machines course. So this is the design of machinery by R.L. Norton. Okay, so the PDF copy of this book is available online. Maybe a bit older version, it doesn't matter. Any version you can download and you can use the book. Only few chapters are important, not that. So the force analysis is important from the textbook. Your learning guide also gives you, but it's possible that your learning guide may have some typo errors. Okay, so this is explained for link 2. So the same way of writing. So the two equations we write is sum of the forces is mass times acceleration, then sum of the torques will be I into alpha. So now these equations you apply to every link depending. So following the notations. Okay, so this is for the connecting rod. So you will have the same three set of equations. Then for the slider or the piston, so you will have three equations. Now combining these three things with any conditions or any known conditions, so we can write in matrix format. So you can see here you get 8 by 8. One equation will be reduced because when you apply the friction condition, so you can actually reduce one equation. Okay, so I try to give you the central concept. So now there's one more. Okay, in the textbook there's one more, and Professor Firoz will be going through one more example. So normally out of this 3 or 4 cases, so you will be asked one. So guys, any doubt or any question?
The force, the arrow, how to determine which angle, like F12. How do you know like which angle is coming from?
You are not considering which angle.
Any direction is fine.
So it is basically your orientation depends on the angle theta 2, right? So theta 2 is not given. Means theta 2 is not important unless until you are doing the calculation.
Okay.
If you want, I can show you some example. normally the examples what they do is they will give you the all the angles, the length of the links, then okay, the basic figure. Okay, so for any question, the basic figure will be given to you. For example, if you are doing a slider crank, so you will be given this position. Now, based on the given orientation, so then you are drawing the free body diagram. So it is up to you to represent the diagram. So the angles. So now, for example, this is focus here. I'll go back to the next slide. Now you can see here. Okay. So this is approximately you draw the link to. Okay. So identify the centroid. It's up to you. Just locate the centroid. Okay. Now from the centroid, now this link is connected to link 3 here. Okay, to the ground here, right? Okay. So now the position of 1 from 2 is directed downwards. So the position vector is downwards. Okay. Now the force acting on 1 and 2, whether you show like this or you show like this, doesn't matter.
Okay.
So because you are not doing a numerical calculation, it's only a representative force. So when you are doing is cross product, okay? So you are just taking the cross product of R12 and F12. So always your answer will be this. But depending on the angle, when you calculate R12x, okay, it will be R12 into cosine theta 2. R12y will be R12 the length. If let us say this length of link is 10, so R12 will be 5, half of that. Okay, 5 into cos theta. If your theta 2 is 30 degrees, then R12x will be 5 cos 30. R12y will be 5 into sin 30. So that is just a number. Alright, so the x component and y component is just we are resolving the vector along x-axis and y-axis. And since you are taking the cross product, so once you simplify the cross product, so the cross product of 2 parallel vectors will be 0. So here these 2 vectors are perpendicular vectors. So the sine theta becomes sine 90 and 1. So therefore you can get rid of the vector form. Alright. I think some of you guys have not submitted your assignment 1. If you don't submit by tomorrow, I think you will be given 0. And without any extension request. So by this Saturday you must submit, otherwise consider that okay, you will be re-enrolling into the module. Because if you can't submit assignment 1, then it will be difficult for assignment. Alright, so we go for a break. Now the time is 8, so we'll come back.